Hello students, let us start our today's session with hydrocarbons. What are hydrocarbons? Hydrocarbons are the compounds of carbon and hydrogen only. And these hydrocarbons are further divided into saturated and unsaturated hydrocarbons. In addition to that, we have aromatic hydrocarbons also. So what is the need of learning hydrocarbons? Hydrocarbons are mainly used as fuels and they are also used in the manufacture of polymers. And the fuels are, we have liquefied petroleum gas LPG, CNG compressed natural gas, and LNG liquefied natural gas. So all these, besides that, we can get it from non-renewable resources. Most of the non-renewable resources are the hydrocarbons only. So they have a large variety of hydrocarbons and they do differ in their boiling point. They can able to isolate by fractional distillation method. So at the different ranges of temperature, we will get the different compounds of carbon and hydrogen, that is hydrocarbon, from which only we are getting petrol, diesel and even kerosene. Kerosene is used as the domestic fuel. Classification of hydrocarbons. These hydrocarbons broadly classified into aliphatic, aromatic. Aroma, pleasant smelling, and aromatic compounds are the benzene and its derivatives. Benzene, it is a 6-membered ring and it has a 3-pi bond and its formula is CnH6. And in aliphatic, we have two classification. One is open chain, the other one is cyclic. Open chain, it is also called acyclic. A means no, that means the open chain compound has no cyclic structure. But in cyclic structure, the open chain structure gets into closed structure. Such compounds are called cyclic compound. And it is further broadly classified into saturated and unsaturated. Saturated hydrocarbons, let us take that cyclic also. This is cyclohexane. For the cyclic compound, we have to give that prefix of cyclo, in which it solves single bond. That means carbon-carbon single bond only we are finding. So the name of the compound, it is cyclohexane. And in open chain compound, we have alkanes. The saturated hydrocarbon, they have the primary suffix of ane, and in which carbon-carbon single bond is alone present. The general formula of alkane is CnH2n plus 2. And this is, if you where you have n equal to 1, you may get the first member of hydrocarbon, that is the open chain, and the saturated one will be methane. And in unsaturated hydrocarbon, we have a doubly bonded hydrocarbon and a triply bonded one. Doubly bonded, we know it has the primary suffix of ene and whose general formula is CnH2n. And in C triple bond C, and in alkynes we have CnH2n minus 2. And in an alkene, the doubly bonded carbon, both of them will get sp2 hybridization, but in triply bonded alkynes, both of the carbon will get sp hybridization. And the doubly bonded or the triply bonded hydrocarbon, that makes a part of the long chain. And the carbon-carbon double bond, carbon-carbon triple bond, that could be present in one form or can be in more than one places. So where we will say di, tri, etc. How many times the double bond repeats, that many times it will be counted and we will tell. This is what? The classification of hydrocarbons. Let us see one by one. Alkanes followed by alkene, alkynes, and then aromatic hydrocarbon. Let us see the first members of hydrocarbon alkanes. So the alkane that makes the homologous series whose general formula is CnH2n plus 2. So hydrocarbon that has n times of carbon and 2n plus 2 times of hydrogen. If n equal to 1, you will get 1 carbon, 2 into 1 2, 2 plus 2 4, so you are getting CH4. This CH4 is having 1 carbon root word is meth and its primary suffix is ane, so the name of the compound is methane. And this methane, it has 4 hydrogen atom. See, all the 4 hydrogen atoms we can replace by any alkyl group. To any length of the alkyl group we can replace. Suppose if I replace this hydrogen by a CH3 group, that is 1 methyl group. The nomenclature in the previous video also we discussed. An alkane is RH group, where H is removed, that R group is said to be an alkyl group. So here I am taking that methyl group to replace the hydrogen. So when I replace this hydrogen by methyl, you find the compound it takes 2 carbon atoms. So where n equal to 2. And the hydrogen becomes 2n plus 2 times. See, 1, 2, 3, 1, 2, 3. So totally it takes 6. So this makes the second member of hydrocarbon, that is called ethane. So similarly, we can have or we can construct to any bulk size of hydrocarbon. And this hydrocarbon, methane I have CH4, ethane I have C2H6. You may find these two hydrocarbon are differing 1 carbon and the hydrogen differed by 2. So each successive member of hydrocarbon, they differ by CH2 group. And this CH2 group is called methylene group. And this methylene group that weighs the molar mass of 14 units. So the successive member of hydrocarbon, they will differ in their molar mass by 14 units. For example, methane I have 12 plus 4 equal to 16. 1 for hydrogen, 12 for carbon. So 4 hydrogen, 4 into 1, 4. So 12 plus 4 equal to 16. In ethane, I have 2 into 12 carbon and 6 into 1 hydrogen. So 2 into 12, 24. 24 plus 6, that is equal to 30. So you may find 30 and 16. The difference of these two values is equal to 14 units. So the successive member of alkane, they will differ by CH2 group, that is the methylene, and they differ by the one with the other, the molar mass differs by 14 units. And in this alkane, all the carbon atoms are sp3 hybridization, carbon whose atomic number is 6. Its valence shell, I can write helium with the inert core of 2s2, 2p2 orbital. And the 2s orbital, it has 2 electron, and the p orbital, it gets 1 electron each. Upon mixing of these atomic orbitals, they do differ in their energy very slightly. It gives rise to the sp3 hybrid orbital of carbon, in which these 2s electron from s orbital and the 2 electron from 2p orbital, it is getting into 4 sp3 hybridized orbital, and each sp3 hybridized orbital, they have 1 electron in it. So due to this sp3 hybridization, the carbon, it has 4 sp3 orbital electron, and these 4 sp3 hybrid orbitals of carbon, that overlaps with 1s1 orbital of hydrogen. Hydrogen, it has only 1 electron and whose electron is present in 1s1 orbital. So that makes that sp3 hybrid orbitals. This is what? sp3 hybrid orbital. So in this orbital, this is the carbon atom. It has 1 electron, 1 electron, 1 electron, 1 electron. And in these 4 single electrons of sp3 hybrid orbital, the hydrogen, it overlaps with 1s1 electron. So that orbital, it gets paired up. So this is with hydrogen, and this is with hydrogen, this is with hydrogen. So there are 4 hydrogen atom that overlaps head-on axial overlapping to the 4sp3 hybrid orbital of carbon. So it gives rise to the sp3 hybridization. As a result of sp3 hybridization, the 4 hydrogen atoms, they take in their regular tetrahedron position and the molecule that occupies tetrahedral structure. In the tetrahedral structure, the central atom is carbon. The central atom is carbon and the 4 hydrogen atoms that occupies the regular tetrahedral, and it has a multiplanar structure. Because depends on the air, only 2 of the group and the carbon will be lying on a plane, the other 2 groups will be out of the plane, one above the plane and the other one is just below the plane. So it makes a multiplanar structure. And in this, the tetrahedral structure, it has a bond angle of hydrogen, carbon, hydrogen is 109 degree 28 minutes. And the carbon-carbon bond length is 154 picometer. And carbon-hydrogen bond length is 112 picometer. And these alkanes generally known as paraffins. Paraffins means, param means little. Affins means affinity. That means it has little affinity towards reactions. That's why alkanes are generally known as paraffins. So it doesn't show the most reactivity towards acids, alkali or any other compound. Why these alkanes are inert? See, the carbon, it has a saturated linkages, and the central carbon that has attained the stable structure of octet. That means as the carbon, it gets 8 electron in its valence shell that satisfy its octet rule, and hence the hydrocarbon, particularly the alkanes, are showing little reactivity towards any other compound. That's why they are inert in nature. Let us see nomenclature. Nomenclature already we have discussed in the basic principles. So what we have to do? The longest chain we have to identify. The longest chain is referred as the parent hydrocarbon. So the longest chain should be identified by numbering the given compound. The numbering, you can start from either of the direction, from top to bottom or left to right or right to left, wherever you may find, you can go. But the substituents should get the least possible number. That only we have to consider. We can proceed the numbering on either of the direction, but the substituent should get least possible locant number. That we have to do. So after identifying the longest chain, we have to find it whether all the carbon atoms are having, what is that, single bond or a double bond or a triple bond. If all the carbon atoms are linked by single bond, then it will get its root word with the primary suffix of "ane." After identifying the longest chain, you have to get the substituent. The chain should have the maximum number of substituents. So such a way only you have to give numbering for the parent chain. And locant number should be the least possible to the substituent. After getting that longest chain and the position of substituents, we have to write the name of the compound. How we have to write? First of all, if the parent chain has any substituent, that substituent's locant number should be given. The locant number, if at all, repeats for the same substituent, you have to put comma between them. And then the prefix, if you have same alkyl group more than one time, then you have to count di, tri like that. If the substituent is only one time present, you can take only that alkyl group name as such. And then you have to go with root word. Root word is the parent chain, how many carbon that contains, from that we will get the root word along with its primary suffix. Here we are finding alkanes, so its primary suffix is ane, ane, so we should end with ane. and the substituents should be called out in their alphabetic order. Let us take an example of this compound. You may find the straight chain, it has 1, 2, 3, 4, 5 carbon in its straight chain. And I am getting the other way. See, 1, 2, 3, 4. Here it gets only 4 carbon. And 1, 2, 3, 4, 5, 6. You are finding this way, you are getting 6 carbon atom. And the other way, I can write 1, 2, 3, 4, 5, 6, 7. There are 7 carbon atom. So we have the possibility of the chain having 4 carbon, chain having 5 carbon, chain having 6 carbon, and the chain having 7 carbon. I said it must be longest chain, so the hydrocarbon that prefers the longest chain of 7. So this is what the 7, 1, 2, 3, 4, 5, 6, 7 are in this way, 1, 2, 3, 4, 5, 6, 7. So in all both of the direction it takes 7. So the root word for 7. So 7 carbon, its root word is hept. So I identified that root word. Now you just find the black letters only, the longest chain, the black numbering only it says about longest chain, either the blue or the green, that is the shortest chain, that we do not refer. So for using that black number 1, 2, the second carbon it has 2 methyl substituent. One more thing, why should I select that numbering this way? Why can't I this way? Reason, in this way if I go, the second carbon it has 2 alkyl substituent. Here if I go, see the second carbon would not have any substituent. So when I start numbering this way, this 2 methyl group will get the position of 6. But what I said, they should get with least possible number. That's why the numbering is start from here to here. So to the second carbon I have 2 methyl group. And the third carbon it has 1 methyl group, and the fifth carbon it has 1 methyl group. So how I have to write? I should write the locant number. So the locant number 2 because it has 2 methyl groups. So 2, 2. And the 3 it has third position 1 methyl group, and the 5 it has 1 more methyl group. So I can write 2, 2, 3, 5. So 2, 2, 3, 5. Tetra. How many times I have methyl? 1, 2, 3, 4. So tetra methyl octane. This is what name of the compound. And the first letter of that name should always be in capital letter. We should write that uppercase of the first letter. So this is what the way how to write the name for given hydrocarbon. We ask you to write a structure for the given compound. Say that 2, 2 dimethyl hexane. 2, 2 dimethyl hexane. The 2 methyl groups are present at the same carbon. That 2, 2 it says the carbon is the second one to which the methyl groups are present. Okay. And this is what the root word hex. Hex means how many carbon? It has 6 carbon atom. And this is ane. It is the suffix. The suffix it says ane. So this must be a saturated one. So from the name, first of all, you have to identify the root word, and you should find whether it is saturated or unsaturated using their primary suffixes, and then what are the substituents present that you have to identify. Okay, let us start right that 6 carbon. 6 carbon should be in a chain. So I should make 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 or 1, 2, 3, 4, 5, 6. In either of the direction, I can write the numbering. So 1, 2, 3, 4, 5, 6. And these are saturated. So all the carbon should have a single bond. So let us satisfy the valency of each carbon atom. What is the valency of carbon? 4. So all the carbon atom should be surrounded by the 4 single bonds. Then Identify the position of 2. This is the second position. What is the substituent present? Methyl. So, the second carbon, it has one methyl group and the same carbon has another methyl group. After filling the substituent, the rest of the valency of carbon is filled with hydrogen. So, let us write hydrogen, 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 hydrogen. And here we have 3 more hydrogen. This is what? The structural. You can write it in a condensed form. This is the CH3 group. I grouped this is as the terminal one CH3. After that it has CH2. So let us write CH2. This is also CH2 and this is also CH2 and this one it has CH3 and this CH3 can also be written like CH3 twice. This is also can be given. So you should take that carbon, it has instead of 2 hydrogen, it has 2 methyl group. You can represent like this. And the other terminal group is CH3. So writing the structure or identifying the name is just based on the root word and the substituent and where the substituents are present. If you get these informations, then it will become much easier to write the structure for the given compound, or you can write the IUPAC name for the given formula. Structural isomerism. We know isomerism. Isomerism is for a given molecular formula, we can able to write the different structural formula. They do differ in their structure as well as they do differ in their physical properties also. So, for example, let us take C4H10, 4 carbon atom. So, its root word is but and it is a saturated one. So, we can write it as butane. A compound having 4 carbon atom can be represented the one where all the carbon atoms are in a straight chain. So 1, 2, 3, 4 and I can make one more isomer for this molecule CH3, CH, CH3, CH3. This is second one. If I try to write one more structure, that is not possible because as it has very less number of carbon atom, that limits to up to 2 isomer. Let us name the one. See, it has a straight chain, it has no branches. So, the name is given N-butane. N means normal, it has no chain at all. And here it is, this structure is nothing but the iso form of the one. So, for which I can write iso, how many carbon? 4 carbon. So, the name is isobutane. Let us take pentane, as it has 5 carbon atoms. So, the name is pentane. So, first thing we have to make a straight chain. So, let us have C, 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 C. 5 carbon I have written. The terminal is always CH3. So, I put CH3. And the middle carbon will have 2 hydrogen only. So, we can write CH2, CH2. This is also CH2. So, in this, let us write the isomer for the compound. First, let us take the first branch CH3, CH, CH3, CH2, CH3. See, 5 carbon in a chain, by taking one of the carbon to the branch is reduced to 4 carbon. Still, we can make one more structure for this CH3, 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 CH3. See that? Now, 5 carbon in a chain, the first one, and the second one has 4 carbon in a chain, and the third one it has only 3 carbon in a chain. That means, when branching increases, the chain length decreases. So, we can say these are examples of chain isomer. So, chain isomerism is the hydrocarbon that has the differ in their length of chain that gives rise to chain isomerism. So, the representation of primary, secondary, tertiary, quaternary are primary CH3, CH2, this carbon carries only one alkyl group. Iso, this is what iso structure along with the primary carbon. CH3, CH, CH3, when it has a primary carbon in it, then it is said to be iso group. And here the carbon, it has 2 alkyl group, so it is said to be secondary. Here the carbon has 3 alkyl group. Number of alkyl group increases, the degree also increases. So it is tertiary. And here the carbon, it has 4 alkyl group, that is said to be quaternary, or it is a neopentyl structure. It is neopentyl. This is tertiary butyl. As it has 4 carbon, tertiary butyl. This is 3 carbon, so we can write isopropyl. And here it is isobutyl. This you can write it as secondary propyl. Secondary propyl. And this is ethyl. That's all. How the alkyl forms of different isomeric structures given. Let us see the preparation of hydrocarbon. The first method of preparation of hydrocarbon from unsaturated hydrocarbon. Unsaturated, C double bond C, or we can write a C triple bond C. See that in this case it requires, we have to satisfy the one more pi bond by a molecule of hydrogen. In alkyne, as it has 2 pi bond, those 2 pi bonds will be satisfied by 2 molecules of hydrogen. So, suppose if the alkene is reduced by the Raney nickel at 298 Kelvin, we will get C hydrogen single bond CH. So, the C double bond C is into CH. That means both the doubly bonded carbon atom gets hydrogen in its structure. And this process actually known as Sabatier-Sundance reaction. And the same reaction that can be carried out even by using platinum, palladium instead of nickel. Those are said to be catalytic reduction of alkene. So let us see the next one. And Sabatier-Sundance we can write more properly as CH2 double bond CH2. It undergoes hydrogenation process in presence of Raney nickel at the temperature of 298 Kelvin. It gives CH3. You are sharing the 2 hydrogen atom to both of the doubly bonded carbon. So CH2 with the H, CH3, CH2 with the H, CH3. And the next one is catalytic reduction. So in catalytic reduction we can say the catalyst, for example, let us take the same CH2 double bond CH2, but instead of nickel I am going to take either platinum or palladium as the catalyst. Here also that hold the hydrogen and it is shared with the alkene system that makes the compound into alkane. So this is what said to be catalytic reduction. Instead of alkene we can even take the compound containing triple bond. See, I have taken propine. It has 3 carbon. So, prop and its triple bond, it makes its suffix of ine. So, here first of all, I am adding platinum or palladium in presence of catalyst. A molecule of hydrogen is added that gives the hydrogen, it shares between the C triple bond C. So, C becomes CH and the CH goes CH2 where the triple bond is reduced to double bond. And one more you are going to add a molecule of hydrogen where it adds furthermore between the doubly bonded. So, it gets CH2 CH3. So, propine is into propane. This formed through the formation of propane. So, in these cases, you are adding the hydrogen to an unsaturated system. So, the process is also known as hydrogenation of unsaturated compounds. So, addition of hydrogen, that is termed as hydrogenation process. The next method of preparation of alkanes from carboxylic acid. So, let us take the salt of carboxylic acid. What is carboxylic acid? Or COOH. This H is replaced by Na. That means the carboxylic acid with the sodium hydroxide, it forms salt of carboxylic acid. So I have taken sodium acetate. This is electrolyzed by water. That means acetate is dissolved in water and that solution is allowed to go for electrolysis, where it gives rise to ethane, carbon dioxide, hydrogen and sodium hydroxide. In this case, during electrolysis of sodium acetate, it gives rise to the cation and anion. This is what the acetate ion and the sodium ion. So the acetate ion being an anion, it is liberating at anode. When it liberates at anode, it follows the free radical process. See that this acetate ion, first of all, it changes, it loses 2 of the electron. 2 times I have taken, so I am losing the 2 of the electron. When it loses 2 of the electron, that oxygen, it gets 1 odd electron from its structure. So this is what further undergoes free radical, that is homolytic cleavage of carbon and this one. So that makes this methyl will take 1 free radical and this carbon will take 1 free electron, and the free electron of this carbon with the free electron of oxygen, that makes a double bond to form carbon dioxide. So I have 2 times of methyl free radical. These methyl free radicals are highly reactive, so they react together, gives ethane. See that I have taken a compound containing 2 carbon, one of the carbon left it as carbon dioxide, but the other single carbon, it gives rise to the higher member of hydrocarbon. So from Kolb's electrolytic method, we can able to get the higher member of hydrocarbon. Okay, what is the reaction at cathode? See, at cathode the water it gets deposited, where water that releases the 2 electron given by the acetate group that accepted by water. Here also the hydrogen, it undergoes hydrogen OH bond, the HOH bond that undergoes homolytic cleavage. So hydrogen takes its 1 electron and other electron with the 2 electron that goes along with OH minus, and this hydrogen free radical that combines to form H2. What about that OH minus? See, I have 2 Na plus ion, that 2 Na plus that is with the 2 times of OH minus, that gives 2 NaOH. So this is what Kolb's electrolytic method. By this we can able to prepare the higher member of hydrocarbon. The next method of preparation from carboxylic acid is decarboxylation, for which we have to make use of decarboxylating agent. What do you mean by decarboxylation? That is removal of carbon dioxide. The decarboxylating agent is sodium hydroxide with calcium oxide in the ratio of 3:1. This is said to be soda lime. So when sodium salt of carboxylic acid is heated with the soda lime, so let us take CH3, C double bond O, OH. First of all, it reacts with the sodium hydroxide to form its salt. So CH3, COO, Na I am getting. This is then treated with sodium hydroxide and calcium oxide, where I will get CH4 plus Na2CO3. See that? I am going to have only the compound, that compound having 1 carbon. So this is just decarboxylation of sodium salt of carboxylic acid. The soda lime is an important reagent that is used to remove the carboxylate group of carboxylic acid. That's why the name is given as decarboxylation. So in which we would not able to get the higher member of hydrocarbon, we can have only the methane. That means even though the carboxylic acid contains 2 carbon, one of the carbon left as carbon dioxide, the other methyl group only is into methane form. The next method of preparation from alkyl halides. Alkyl halides are generally represented by RX group. So this is done by reduction with nascent hydrogen. What do you mean by nascent hydrogen? Nascent hydrogen means the birth state of hydrogen, it is in its atomic state. The atomic state of hydrogen is highly reactive. See, to produce the nascent hydrogen, we can make use of either of the reducing agent. Metal acid, metal liberates hydrogen, or metal with the acetic acid. Here also you can get hydrogen, the liberation, or zinc copper couple in ethanol. This is also liberating hydrogen, or we can have the reducing agent of lithium aluminum hydride. So these are the sources of hydrogen. So by making use of either of the compound as a reagent, that ethyl chloride can be converted into ethane. So CH3, CH3. Similarly, you can take propyl chloride, that is into propane. So what happened to the chlorine? The chlorine is removed as HCl. So by taking an example of propyl CH3, CH2, CH2Cl, either of the agent, let us take zinc HCl, we will get CH3, CH2, CH3 plus HCl. It produces two hydrogen atom. The one hydrogen with the halogen is left as HCl, and the CH2 is satisfied with one more hydrogen. So we will get here it is propane. The previous case it is ethane. So this is what from alkyl halide. From Wood's reaction, just I would like to say one more information. This method is useful for two similar alkyl halides. If you have two different alkyl halides, say one is CH3Br, the other one is CH3CH2Br, it gives rise to the mixture of hydrocarbon. CH3Br with CH3Br, that makes ethane, and that ethyl bromide, that makes butane, C4H10, and methyl and ethyl, that forms C3H8. See that? When two different alkyl halides taken in Wood's reaction, it gives rise to the different products of hydrocarbon, and none of them will be in a better yield. So Wood's reaction is not preferred for two different alkyl halides. In Corey-House mechanism, the higher alkanes are prepared from alkyl halide. So let us take CH3, CH2Br. It is bromoethane. It is treated with the reagent of dimethyl lithium cuprate. This dimethyl lithium cuprate is the specific reagent used by Corey-House mechanism only. So here it is converted into the ethyl into propane. So CH3, CH2, CH3. I have one more CH3, that is with the copper. It gives methyl copper, and lithium with this Br, it forms lithium bromide. So in Corey-House mechanism, we can able to get the higher member of alkane from its alkyl halide. In this, the reagent used for the reaction is dimethyl lithium cuprate. Okay, we have completed classification, nomenclature, isomerism and preparation of hydrocarbon in today's session. Let us see the next session with its chemical properties, physical properties and their conformational analysis and all. Until then, bye bye.